So first of all, let me thank the organizers. Thank you. And so my name is Cristiano Capone. I'm a researcher at the Italian Institute of Health, just a few kilometers from here. And today I want to talk to you about non-synaptic learning. Okay. But first, let me talk to you about synaptic learning. Okay, learning with plasticity. And let me do this by illustrating a very simple task. The task of learning a specific, can you see the pointer here? A specific target output as the linear readout of the internal activity of a recurrent neural network. Okay, so to do so, what I can do is I can update the, sorry, but I, I wanted to go on the screen. Okay, so what I can do to learn to reproduce this trajectory, I can update the readout weights here. I don't know whether you can see. Yes, by following the gradient of the error function. Okay, and updating the weights. Okay, and you can see that the result is that after some time, the output of the network gets closer and closer to the target output. Okay. So this is one way of thinking of learning, okay? So you update the weights, the parameters, with some plasticity rule, some learning rule, okay? But then there is something very interesting happening in transformers. So disclaimer, I don't want to talk about transformers. I just want to, to show one very interesting property here, okay? So if you train large enough transformers on natural language, and then you ask to perform a new task, for example, translating from English to French, okay? So the transformers will be capable to solve this task with some level of accuracy. But if you provide more and more examples here, you can see that the accuracy gets higher and higher. This is a learning curve. But what is remarkable here is that the transformer is capable to do so without changing any parameters, without changing anything, any weights, anything in its structure, okay? So this is one possible definition of in-context learning, and this is also what I mean with non-synaptic learning, okay? So but the question is, how does it happen, and can we induce this in-context learning in other architectures? So one way to understand the mechanism is thinking to this very prototypical task. This is a context-dependent association. So you have to associate this card to one of the two here by shape or by color, okay? So you pick one rule, and if you get the positive reward, you keep the rule trial after trial. But when you get a negative reward, you switch the rule, okay? So one simple solution to this task is you can design two-level networks, okay? So one network here receives information from the reward, okay? And produces contextual information, okay? When the reward is negative, the context is switched. Then there is a low-level network which receives this information from the high-level network, and together with the sensory information, this network will be capable to solve the task. So here, the network is adapting without changing any parameters, okay? So here, the network is adapting in context. So this is simple to understand in this simple task, but can we generalize to other tasks? Can we generalize to any task? So we propose a simple approach, which is basically to replace these weights and learning mechanism with these two networks, right? So there is one network which is receiving the error, okay, and producing the weight updates following the gradient, okay? And there is another network which receives the new weights and estimates the current output of the network. So basically, the two networks has to approximate the linear readout, so the orange one, and the gradient, okay, the green one. So there are no longer physical weights, but rather they are virtual weights which are encoded by the activity of the first network. And as you can see sketched by this figure here, this architecture is capable to learn in context a new trajectory. So now we can extend this approach to reinforcement learning. In particular, policy gradient. We consider this very simple task, which is a reaching task. There is an agent starting from the center. It has to reach an observable food and only gets the reward when the food is reached. And trial after trial, the policy is improved and you can see the reward increases until it reaches an optimal values. So as before, we can create this architecture with two networks, one receiving the reward this time and producing the new virtual weights, and one receiving the virtual weights and estimating the updated policy. Okay. So to do so, we need to first retrain these two networks, okay, to estimate the the gradient and the policy estimation. And we do so by pre-training on some specific position, demarked by the red crosses here. And if we test on new position, the network is capable, this architecture is capable to reach to the generalized out of distribution. So basically, the network distilled a strategy to reach any possible food position. Okay. So what I didn't tell you here is that this network have neurons which are composed of two compartments, one receiving the sensory input and one receiving the contextual input, and they interact in a non-additive way. This we call gain modulation. I finished. And if we remove gain modulation, the network is not capable to generalize out of distribution. So I'm done. So take-home message is we propose a constructive way to induce in-context learning in recurrent biologically plausible neural network, and gain modulation is a key ingredient.